All right, and we are back. Last episode, we went through the documentation to figure out what all of the tables mean that we have in the font file we are trying to use and parse. And we decided that the CMap table is the table that we want to parse the most right now. And so what I'm actually starting to do is I'm gonna tag the version of the project for every at the end of every episode so that I can always go back to what the code looked like at the start of an episode or end. And that's cool. So what is next? Actually, what is next is I'd like to add this little thing here, the GitLab continuous integration, so that it stops automatically detecting that I am building a Heroku web app and complains about it. I get a bunch of emails, which isn't nice. .gitlab -ci, is that what it's called? Oh my lord. Oh. .gitlab.ci.imyml. Ooh. Hello? Hello? Alright, and then... Oh, I love my Git, but Emacs is just driving me crazy. Yes. Absolutely. We want to create a file called .gitlab-ci.yml. No, we don't want to install that. Paste, save, commit it, add GitLab CI file. Right. That is one thing we do. Delete the buffer. Right. So we have that now. We can merrily continue with this. No, not this. No, not this. CMap table. So there's a whole bunch of formats. I think we're not going to bother trying to figure out what all of them do. Just want to get to a minimal working example as fast as possible. So we're going to try to figure out what format we are using. We've already parsed a good part of the thing. Where is it? Raw table records, and then head table, no, CMap table. So these are the encoding records. So we have 0 means Unicode, and there's a encoding ID 3, 4, 5, and that's it. The rest is Windows and Mac specific. And it looks like this 52 offset is the same for Windows. It's just Mac that has its own little encoding, but we don't want to be, we want to be cross-platform, so we're just not gonna bother with those. Well, yeah. I think, doesn't every operating system currently use Unicode to encode their text nowadays? I think that's mostly true. I wouldn't know why anyone would want to deviate from that, since it's a standard that's good enough and actively maintained and developed. Right, so as this mean encoding, we know the platform is Unicode. Unicode variation sequences supported by the font should be specified in the CMap table using a format 14 subtable. A format 14 subtable must only be used under platform 0 and encoding ID 5. Oh wait, format 14 subtable, what's the encoding ID? Oh my lord. I don't. Format 14. So platform specific encoding ID. The encoding record entries in the CMAP header table must be sorted first by platform and then by its platform specific, and then by the language field in the corresponding subtable. Okay. 3, 4, and 5. Platform, each platform. The name table chapter. Ah. Oh. Let's read this. Naming table allows multilingual strings. Many newer platforms can use strings intent for different. Naming table header, format, number record, string offset, name record, storage of string data. Okay. There's 2 formats. And then each lang tag, blah, blah, blah. Name records. Each string in the string storage reference by name record. Record has multi-part key to identify the logical type of string and its language. Alright, here's the platform encoding a language ID. Is a platform. Except in conjunction. I love exceptions. Language ID. Value less than 8,000 in hex. I'm gonna find format 0. Well, these are the platform IDs. Unicode, Macintosh, ISO is deprecated, Windows, and custom. Thank God we don't see custom. Platform ID 2 is deprecated, are reserved. What? Alright, so you can use those if you need to do something funky. We don't. Platform encoding, language IDs, Unicode, platform ID 0. So this is what we have. These are the encoding IDs. Unicode 1.0 semantics, 1.1 semantics, something. 3 means Unicode 2.0 and onwards. Unicode BMP bitmap only. CMAP subtable formats 0, 4, and 6. Oh, what does this mean? Unicode BMP. Let's have a look. Unicode BMP. In the Unicode standard, a plane is a continuous group of 2 to the power 16 code points. There are 17 planes identified by the number 0 to 16, which corresponds to the possible values of the first 2 positions in 6-position hexadecimal format. Plane 0 is the basic multilingual plane, contains most of commonly used characters. Higher planes are supplementary. 6 of the planes have assigned code points and 4 are named. The limit of 17 planes is due to UTF-16, which can encode to the 20th points as a pair of words plus the BMP as a single word. Alright, so 16 bits. Whoa. Hey, that's not fair. Then how do we know we have a multi-byte? Is there... Wait, doesn't the 16-bit... Like, UTF-16, doesn't that have some sort of sentinel value or a bit that can be set? Pair words. Well, whatever. UTF-8 has a much larger limit. So yeah, there are still 13 or 137,000 things that there's like a million unassigned things. Fine. Unicode blocks. So the BMP plane is the basic multilingual plane. I'm gonna write that down, I guess. BMP, where are we? We are looking at CMap. I really want this to be here. Wrap it. And then also encoding. Encodings. Get a link. Is that? That takes so long to insert. So that's where we can find the information if we want it in the future. And then encoding 4 means Unicode full repertoire. CMap subtable format 0, 4, 6, 10, and 12. And then Unicode variation sequences. What does that mean? Format 14. What is a variation? A variant form is a different glyph for a character encoded in Unicode through the mechanism of variation sequences. Sequences in Unicode that consist of a base character followed by a variation selector character. Variant form usually has very similar appearance and meaning as its base form. Mechanism is intended for variant forms where generally in the variant form, if the variant form is unavailable, base character doesn't change the meaning of the text. May not even be noticeable. Okay. Standardized ideographic. Are the records all relevant? Do we need to parse all of them? Do we need all of it? Do we need to, if we, let's say we have a glyph, and we have a glyph, or a character, or like an encoded character, and we want to figure out what the glyph is for that character that we want to use. Do we then need to try multiple encoding records, tables, things? I don't know. Semantics. I think we kind of want to look at how many bytes are in here. Oh no, that's just the offset. Oh gosh. I really do not understand how this works. What can we do? Subtable formats. So the platform plus encoding IDs do not specify one format. So how do we figure out the format? Yeah, well, this makes sense. It's just the following are currently defined. All right. I don't care. So using the use of the language field in CMap subtables. Oh, they all start with a format. No. Yes. What's that? So let's try to have a look at the formats for all of these. We're just gonna read the first 16 bits at the offset. Let's try to do that. Maybe what we can do is try to... I suppose we don't have to. Alright, let's do it here. Let's hack it in. We have the CMap, and now we're gonna look at the coding records for in. Yes, we will do encoding record dot offset. Oh, yeah, well, that bytes is equals meta dot CMap bytes at the given offset. That equals from that as a use size offset to, how do we know the length? We don't know the length. Do we care? I don't think we want to limit it to anything. We construct a slice over that. Is this wrong? CMap bytes equals root meta dot CMap bytes dot unwrap. Oh, it's a 32-bit number. Cool. And then just like that. That's unused. Good. And then we do bytes.consume single. We want to read a format, which is a U16 big endian. And we want to okay or parser expected end of input bail out if we fail. What's the issue? Expected struct font reference. Yeah, we can dereference it. Make a little copy, and then we just print. We will print the record version format encoding record and that should be good. Can kind of leave that out. Also this one. That. Right, what are we seeing? Table record. Oh, this is because we're looking at that. We added the debug statement in here. I kind of delete it. Well, it's useful. We'll clean it up later. No problem. Ah, there we go. All right. So we have a platform ID Unicode, encoding ID 3, and then the format of the table is 4. That makes sense. Format 12 and 14. 4, 12, and 14 are the ones we're interested in. And let's have a look at them. Sort of write it down. Format 4. Segment mapping to delta values. This is the standard character to glyph index mapping table for the Windows platform for fonts that support Unicode basic multilingual plain characters. See that above for details regarding subtable formats for Unicode encoding on the Windows platform. The format is used when the character codes for the characters represented by a font fall into several contiguous ranges, possibly with holes in some or all of the ranges. That is, some of the codes in a range may not have a representation in the font. The format-dependent data is divided into 3 parts, which must occur in the following order. Format-dependent data is divided into 3 parts. A forward header gives parameters for an optimized search of the segment list. Forward header. Then for parallel arrays describe the segments. So it's like an array of struct of arrays probably. Describe the segments, one segment for each contiguous range of codes. Wait, how's there 4? Can there only be 4 segments? A variable length array of glyph IDs, unsigned words. Yeah. Okay. Let's have a look. Struct cmap. I guess it's a raw cmap format 4. Format, but we already parse it because we want to determine the type of table. And of course, if you're using C, you can just define a union and then look at the format and decide how you're gonna index into the thing. But because we're working with slices and we consume based on the size of an object, we can't do that with our approach currently because we want to check that we're not going to read past the end of the file. We have to check that it's within limits. So what we do instead is we look at the format and then we consume the right format, and it's going to check if it's within the bounds, which is the right way to do it, I think. But it does make us separate the format, which is a good thing, because why do you want to store the format in something if you're requiring the format to be a certain value? That's just wasted storage. So let's not. But we are going to define it. Format of type U16 big endian equals 4. Oh, actually what I can do it like this. That type is a 16 big endian from native endian 4. Well, I can have associated constants on. I cannot. I can. Can I not? Well, whatever. Length in bytes of the subtable. There is language. There is seg count times 2. There is search range. There is the entry selector. There is the range shift. I've seen this in the range shift is also defined in the header of the entire file, I think. End code, which is oh, this is bad. Seg count. Start, and then we're gonna have end codes format. Struct raw cmap format for end code. And then pub struct. So raw cmap format for start. Then we have end code is a U16 big endian seg count times. It's sort of, oh no, reserved pad. There's a whole bunch of arrays, so there's no reason to. We're gonna parse them one by one. We don't need the end thing. CMap format 4. So variable length stuff. Okay. Then we're going to write our CMap format for struct, which will have a lifetime, have the header, Role CMap format for header. Do we want to provide a reference to it or copy it? I think in this case it makes sense to copy because it's relatively small, and otherwise you'll be doing so much indirection and you're probably gonna access those values quite often. So we're gonna save that, do that by value. Pub. And then we have to copy clone. All right, what do we have here? We will be reading end codes, which will be your reference to use 16 big endians. Then we will have reserved pad, which will be a uint 16 set to 0. Then we will have start codes, and then there's going to be delta, ID delta, which is also an array. Whoops. And then there's going to be ID range offset. Now, I'm going to try not to worry about the performance of how I'm doing this. You will probably want to sort of convert it into a structure that is easier to search with less indirection. But I think for now, we're going to have to do profiling to figure out if that's actually an issue. And also, it's very likely that the way I'm writing the code will change at some point, although I hope not. So the ID range offsets are also unsigned. The ID deltas are actually signed. And then there is a glyph ID array of arbitrary length. Glyph ID array. We don't know how long that is, but it's going to be composed of 16-bit unsigned integers in big endian. Number of segments is specified by seg count, which is not explicitly in the header. Wait, it's not? It's times 2. However, all of the header parameters are derived from it. The search range value is twice the largest power of 2 that is less than or equal to seg count. The search range value is twice the largest power of 2 that is less than. So the largest power of 2 that is less than or equal to seg count. Yeah, okay. That's like the next power of 2 divided by 2. For example, if seg count is 39, then the largest power of 2 that fits must be 32. Seg count times 2 is the double. Search range is 64. Entry selector is log 2 of 32 is 5. That's the actual power. And then search range shift is 14. So range shift in what direction? How do you... Okay, let's continue reading. Each segment is described by a start and an end code, along with an ID delta and a ID range offset. I am just on a site as a side note, I am confused as to why these This is not an array of structs, the start and end codes and all that stuff. Maybe you don't always want to read all of it. That is the only reason I can think of that you would want to separate it. Or maybe then the offsets become larger. But then you can just multiply it by... Yeah, I don't know. Maybe we'll figure it out at some point, but it is how it is. Each segment has a start code, an end code, an ID delta, and an ID range offset, which are used for mapping the character codes in the segment. The segments are sorted in order of increasing end code values. The segment values are specified in 4 parallel arrays. You search for the first end code that is greater than or equal to the character code you want to map. So you find the upper limit, the first one, so the least large end code that is larger than the character. If the corresponding end start code is less than or equal to the character code, then you use the corresponding ID delta. Oh, that makes sense. So we have an upper bound. We defined the ranges to be from start to end. And because they are sorted, the end codes are sorted from low to high, we can find the ranges will not overlap. Or can they? I don't think they can overlap. That wouldn't make sense. You want to map, you want to have one mapping for one character should map to one glyph, right? And then maybe the variations are defined. Okay. So what is the value of the start and the end? They're UN16. Glyph ID array. Maybe what we should do is parse this thing and then look at the values that will help us determine how to do things. So we will implement parse for this thing. Bytes takes that, returns result of self or a parse error. And then this is mutable. So first we write the let header equals cmap format for header bytes.consume single dot okay or error parse error, and expected end of input unwrapperino. How is this wrong? Raw. It's not implemented. We have a reference, but we kind of wanted to dereference it, and now it's saying it's not implemented. Implement unsafe from raw bytes for raw cmap format header. All right. and then we need to return the right thing. So we have the header, and then we will do let end codes let seg count equals header dot u16 from header dot seg count times 2 as a use size. Oh, I can just divide it by 2. What's the reason for having that times 2? I don't quite understand. I don't. Yeah. Right, so we find the seg count, and then this is simply we can do this. We return CMap format 4 and codes is going to be bytes.consume slice seg count. Okay, or parse error unexpected end of input. We have encode, reserved path, start codes, delta range, glyph ID. Single pad glyph ID array. What's wrong with this? Ah. How are we doing? You have to dereference it. What's the issue? It's not public. Right. Now, dang, this is so much stuff. So many new types to create if we want to do it right. Also, we're going to be, every time we index into one of these slices, we're going to be doing bounce checks, which might suck really bad. Because we kind of want to verify that the offsets are in range and then do it. But it's very hard because that, if we try and do like get unchecked and trust the offsets, then we have obviously vulnerabilities in our code where a carefully crafted font file can actually read from memory locations outside of where it should be reading, which could be problematic, could be exploited. So we don't want to do that. So we're just going to be inefficient and profile and see if we need to change something. For now, I want to print this. Oh, the problem with printing slices, though, is that it's going to print everything. I don't like that. Let's just print the header then. Header then. Or let's just print it. Let's see what it does. Hopefully it doesn't block. Alright, so if format equals cmap raw cmap format for header format, we will do cmap format for parse bytes, the remainder. Sub equals that, and then print line sub. It's getting late. I'm getting tired. We want to compile this. We want to run this project / OTF lab, and then cargo test. Right. This is all the data. That's not too much. It's manageable. Start code reserve pad. These must be the. It's interesting that they have the encodes first. So there's a range from 47, no, to 47 from 32. 32 to 47. So that must be like ASCII. Let's look at that range. 47 slash. That's a slash character. What is where 20? Where does it start? 32. File separator space. So we have a group from space to slash, and then from 48 and 58. 48 probably to 58. It's inclusive. It is inclusive. Encode is inclusive. It's good to know. 48 to 58 or 57. So that's the numeric characters. And there's another range. So actually this is not very optimal because these ranges overlap. Oh wait, no, they map to different places. Wait, what? No, they should map to the same Unicode. All right, let's think about this. We're mapping from character codes. It's like apparently 16-bit integers. So how do we represent (32-bit) Unicode values? How does that work? Oh, probably different format table. Duh. This is just for the basic multilingual plane. That's why there are 16 bits. Makes sense. All right, so let's decode this by hand. Let's say we're trying to figure out the glyph for a 0. We have character code 48. We start going through the end codes. And we're like, all right, 48 is more than this. 48 is less than this. So it has to be within the second range or we don't have a character for it. So we go look at the corresponding index in the start codes, which is 48. That happens to be exactly the character we're looking for. So we're going to look at the ID delta, which is 829, and the offset is 0. ID delta is 829. Alright. So the character code is 48, 0. And then the segment index found is 1. The ID of offset equals 829 ID delta, I mean. Zero. All right, let's go back to this. Now the glyph ID is computed. I honestly, I cannot believe that this is all happening for every character on your screen. Every time we need to figure out how to render it, like disregarding caching, we need to look up the glyph ID by searching ranges for every character. I bet there's some like crazy multiple instruction, no, single data, multiple data, single instruction things going on. SIMD, single instruction, multiple data, optimizations being used to do all the searching for multiple characters in parallel, or I have no idea, but probably in the, it's probably pretty optimized in the existing rasterizers, this sort of thing. I'm surprised. But yeah, what do you expect? I mean, if you have a huge character range like that, you can't just use a table. You need to have a more compact mapping. It's kind of like a custom hash table, honestly. All right. Let's read. If the range ID offset for the value is not 0, mapping of a character codes relies on glyph ID array. The character code offset from start code is added to the ID range offset value. This sum is used as an offset from the current location within ID range offset itself to index out the correct glyph ID array value. This obscure indexing trick works because glyph ID array immediately follows the ID range offset in the font file. The C expression that yields the glyph index is dereference ID range offset I, where I must be the index that was found, like the correct segment. It's like the range index. So then we find the range offset divided by 2, add the character minus the start count. So this is basically just the index of the character within the range. That makes sense. And then we also add the address of the ID range offset I. So we're offsetting from the ID range offset. So what's the advantage of doing this? Like, why are we offsetting based on this? No, based on the address. That's just adding I to this. The start of the ID range. Why does that? So like the address of this field, the offset of this ID range field plus seg count plus the index of the character within the range plus this value divided by 2 is the index of the glyph in the dynamically sized glyph ID array. And I find that an extremely odd way of indexing. I don't yet understand why that happens, but figuring that out is something for the next episode. Thank you for watching as always, and I wish you the best. Bye bye.